Boom. Hello and welcome back to Precalculus1, section 1.6, Transformation of Functions, part 2. We haven't looked at all of the concepts, so let's first see what we did so far. We did horizontal shifts, vertical shifts, so vertical shifts, horizontal shifts, and we did reflections. So we did 4 out of 6. What's left is to discuss the horizontal and vertical shrinking and stretching of a function. You understand that certain things you can stretch without ripping them to some extent, right? So as you can see, this is where the end of the rag is, and if you stretch it, right, now it's longer, right, and didn't break. If I try to do the same thing with the paper will rip. So we can stretch vertically and we can stretch horizontally, and then we can also combine the two motions right in the same time. So what I'm going to do is define these guys. So let's do the vertical stretch. We are achieving vertical stretch when we multiply a function by a number. So simply if you say 2x, because it's times 2, it's vertically stretching. 2x squared or 5x cubed or 5 times square root of x. It is not humanly possible to do an extraordinary job in graphing some of these functions, and it's sometimes hard to see how this works. So if I say y equals x, it's difficult to see the stretch because it will look like the function was rotated, right? If you say y equals, say, 3x. So this one would be the 45-degree line, which is the parenting function, and then this one would have a slope of 3. So this seems like it was rotated, but it wasn't rotated. What happened was that each point is now times 3. That's what happened, which is exactly what you had in the equation. So what I want to do is explain these functions in terms of functions that you haven't seen and you will not see until Precalc 2, which are sine and cosine. Your book is doing the same thing without telling you those are sine and cosine functions. The best way to see this stretch and understand the vertical stretch is to think of a function that looks like a wave because you have experience with a wave. If the wave is 2 times as large as the one you've seen before, you have that concept in your head, right? You know what it means. So if you start with a function y equal sine x, again, you're not supposed to be memorizing these things. You're supposed to be understanding what's happening. We would draw one representation of that wave just like this. And then if I decide to multiply by 2, then the new graph will be like this. So I hope you see that this is vertically stretched. The function didn't move or shift or rotate, didn't do any of these things. What happened was literally this, right? And now, so rag used to be like this, and now it's twice as tall. You can work on, let's say, y equals square root of x, and then y equals 4 square root of x. In which case, you have the parenting function, and then you have the one that it's 4 times up. So it's vertical stretching. If you use a fraction between 0 and 1, you will be shrinking vertically. So if I go and say y equals sine x, but then you put 1/2 in front, then in that case, it's not a stretch, it's a shrink. So if this was our original graph for the sine, the new one will go halfway through it. So you can think about this idea while looking at the graph, where the one on top says, here is your wave. Now this would be, you cut the ocean sideways and you see the waves going like this. This actually models the surface of that. So you see the wave coming in, and then more wind somewhere out there makes this wave larger, right? So the wave, and then twice the size of the wave and half of the size of the wave. So you can see that this top point is twice as tall, because this was 2 times, it was times 3, it was 3 times as tall, and so on. And now you're cutting it in half and so on. You will obviously cover all of this again when you go into pre-calculus course and actually learn about trigonometric functions. Now this all obviously holds for all of the functions that we want to study, but our functions are not as easy to see with these types of transformations that trig is. So it's awesome. Y equals, say, 1/4 of absolute value of x. Well, I'm going to draw the default case in black dotted ink, even though this is not ink. And then 1/4 is going to be that. So as you can see, I'm shrinking the function if I use numbers between 0 and 1, if I use numbers larger than 1. Now, do I get to use negative numbers? Do I get to use negative numbers? Can I say -3? And what would that do? Very good. We don't get to use the negative number to associate one thing to it, because the negative number, if you stay -3, -3 is actually the negative and number 3. Number 3 is going to make the function 3 times larger. The negative sign is going to flip it, which is our reflections. So we only talk about positive numbers making these graphs vertically stretch or vertically shrink. And if you have a negative in front, it will flip it on the x-axis. So it's actually a combination of 2 transformations if you have the negative over there. Same goes for horizontal stretching, which ends the lecture technically. We have to do combined problems. So horizontal stretching, and that's going to be f of cx. So you are multiplying x directly. Again, the best one to use to see this would be, again, trig function. So I'm going to start with f of x equals sine x, but then I am going to put number 2 in there in red. So I'm going to draw the original function, the original wave. And then this 2 is going to compress it, so the whole motion will actually end sooner. So we have, observe that I'm keeping the same height, right? The height is the same, right? That should be the straight line right there. So the height is the same. What happened was that the function was, you know, the accordion, right? That's what it did, right? It smooshed it. This is very difficult to see on functions that we want to consider. Yes? You have to. You have to. Yes, you can do that, but it's really tedious. Generally, we don't care that much because the graph is a sketch that you need to refer to. Technically, we rarely read information off of the graph because the graph is a quick sketch. We actually take a look at the graph to find our increase, decrease, min, max, but then we compute the exact locations using algebra and calculations, right, that accompany those types of problems. So, you know, knowing graphing, the horizontal and vertical stretching and shrinking is the least important and the least useful in the realm of graphing. So the first four you absolutely must know because those carry technically, you know, 95% of graphing. And these two combined, they don't change things much for us to consider. Yes?
Wait, so that won't be like shrinking because it's getting smaller?
It is shrinking in this case, yes.
So 2 means it's multiplied by 2.
Well, x is multiplied by 2. So x is multiplied by 2, so it ends being faster. You will learn more stuff about this in your PreCalc 2 class and then physics and so on. But yeah, in short, in this case, I'm going to draw another example and then we're going to focus on other stuff. So let's take a look at the function g of x, which has sine of 1/2 x. In this case, you are looking into doubling the period. So it's going to stretch like this. So that's what g of x is. So the original one. Now there are going to be measurements here. This is 2 pi and so on, but that's all for PreCalc 2. We don't worry about the actual divisions and so on. You'll have plenty of that in PreCalc 2. So you've seen all 6. The questions that you are going to work on in your later coursework and obviously exams are going to have combinations of these. So you are looking to shift something left, up, and reflect, or do 2 reflections and 2 shifts, or a stretch and a shift and a right. So at least 3 or 4 of these at the same time, because that's how functions behave. That's all it is, or that's what functions. No, that's how. I don't know. Whatever. Let's take a look at an example which will have multiple of these things. Say f of x is equal to 2 square root of negative x minus 1. So how many transformations do you see? 3. What are they? Anyone? Vertical stretch, okay. So times 2. We're going to make it taller. Great. What else? 1 down. Good. And? On y-axis there. See? It's a 50-50 chance you will guess. Just take a stab and see what happens. All right. Over here, vertical stretch. Over here, reflection on y-axis, and over here down 1 unit. My recommendation to you is to use vertical, any kind of reflection first. That's the best practice. Write that down in your notes. Reflections first. Then shift and stretch and do other things. I also told you that on the exam, I am going to provide you with 6 grids. So your exam will have the question like this, and then there will be 6 graphs with divisions and x and y axis, right? Like this. And you are going to have 6 lines on which you are going to write the functions. So I'm not going to do those lines now. You are going to start in the first box with the default case. So the first box is for the default case. The next box is the first of transformations that you want to use. Now, I already told you that if you have the reflection of any kind, or both of them, reflections are first to be done. So, reflecting on the y-axis, box number 2 should have this. Now, I like to write y equal root x and y equals square root of negative x, because this helps me follow which transformations I've done and which ones I still have to do. Now, for the grid number 3, I'm going to say vertically stretch this 2 units up. I will go to the previous graph, look where I'm at, and then I will take that shape and vertically stretch. So you see that the old one was like this, right? I'm not going to keep it there because the old one is on the previous graph. So this over here is going to be y equals 2 square root of negative x. So it's a progression, right? It's progression. We drew the default state, then we flip that default state on this graph. Now this is our new state, and then this line times 2, so each point of y value times 2 creates the new set of dots which connected are this picture. Now, all I need to do is to take that last graph that I have and move it 1 unit down. So, this is -1, and I still have the same shape. Did I say no coffee? There we go. Observe that the last 2 grids are going to stay empty because I ran out of transformations. Right? I have 3 transformations plus default state is 4 graphs out of 6 are populated. Slide. Reflection on y-axis. I would say that's clearly on, but then it's not. So yeah, it looks like inverse CU. Reflected C on y-axis. Right? This is the reflected C on y-axis, and then this is U. Good. Another example for you guys to enjoy. Say g of x is equal to negative x plus 3 cubed plus 2. Right back. How many transformations? 3. Very good. What is the main function? X cubed. Have you memorized what x cubed looks like? You did. You better, right? Because that is the learning in this class, right? Student, studying, learning, right? I provided you with a list of functions that you must know. Those are the default states. And this stuff builds on those. If you don't spend time learning and drawing the default cases, clearly you are going to be lost and paralyzed with a question like this. You might be able to recognize reflection. You might be able to recognize shift to the left and shift up. Perfect, right? That's great. But if you don't know what x cubed looks like, all of that is irrelevant, that you can realize what these things are. So we start populating our first graph with x cubed graph. This is just x cubed, and we are done with the first graph. The next graph is going to introduce the reflection on which axis? X-axis, yes. So it's going to reflect on the x-axis. The graph is going to look like this, which is now negative x cubed. Now, I'm going to move this 3 units to the left. That means that the good old point that went through the origin is now going to go through -3. We keep the same shape of the graph from our second box. So it's the same shape. It's now a -3. And finally, in the last step, so this is over here -x plus 3 cubed. And finally, we are going to raise the graph up 2 units. So you are going to go to -3, go up 2 units, and this is where the squiggle will switch now. Now, if you're interested in full credit, you will label this point as -3, 2. Otherwise, don't worry about it. So you see the progression, and you also see the progression in the formula and how you build up to the point where you have the graph shifted. You start from default, then we reflect it, then we move this shape 3 units to the left to get that graph, and then we took this graph, which was at 3, and shifted 2 units up because of +2 at the end to come up with the latest graph. Yes?
Why did you shift 3 to 1?
It was +3.
So then you carry over it's actually -3.
+3 goes to the left, yes. +3 goes to the left, -3 goes to the that is not obvious. You say, why is the plus shifting up and minus is shifting down, and now all of a sudden, right, the plus is shifting to the left, and right, you want it to go to the right. Well, the one that is backwards is actually up and down. That's the one that is backwards. If you remember your algebra and you remember the formula which was called point slope, do you remember that that formula was y minus y1 equals to mx minus x1? Do you remember this formula from your intermediate algebra? You should, because this is the formula. If you have a point and you have a slope, you put the point and the slope and you have equation. Observe minus y1 on this side. You see that? Would you agree that if I put this y1 to the other side would be plus y1? Right? Now, plus y1 on this side, plus y1 would shift things up, which means that minus y1 on this side shifts down, shifts up as well, sorry. So when y's are actually together, the shift actually works the same way like the horizontal shift. It's a little bit, you know, but this is the only example you know so far. So that's why you might understand that negative actually is shift to the right, and negative is shift up if the y is on the right side, the c, which was right. You are going to understand these things and see them much better when you start exploring. If you are only working the assigned exercises and moving along, obviously, there is zero exploration in that case. You will never get to the point to realize such a thing. Also, another example that you guys have was example for the equation of the circle, which said x minus h squared plus y minus k squared is equal to r squared. This is a formula which we are skipping. We are skipping this formula in 1.9 because you are supposed to know this formula. I know you're excited, guys. It's okay. It's fine. It's math. I'm excited too. You're skipping this formula in 1.9 because you know it from algebra. Hopefully you will read it again. Now, what are the h and k? coordinates of the center. And this is shift right, and this is shift up. Shift up with the minus sign. So when they're on the right side, they always have the opposite behavior of what you want it to be. So I will give you the example of y minus 3 is equal to 2x. Believe it or not, this is a shift up, because the number is on the y side. If you move it to the other side, it's still shift up. Doesn't matter on which side of the equation it is. But what I'm trying to bring across is that if x and x shift are together, then, which is a horizontal shift, then minus goes right and plus goes left. If y and the y shift are on the same side, minus is up and plus is down. But because we put the plus 3 and all of that on the side of the equation, it seems that plus is up and minus is down. It is. But you can also have it on this side, and it will do the same thing. So this graph is 1, 2, 3, and then slope 2 through it, whether it's written this way or that way. It takes exploration and time and thinking, effort, sweat, blood, tears, and calling a friend and everything, scream and yell about this, to realize these kinds of things. So now, to recap the entire section, we have 6 transformations. We have the shift, horizontal and vertical. We have reflections, one on x and one on y. And we have horizontal and vertical stretch, or shrink. And we can have, as you can see, combination of these. I hope you wrote in your notes that the first transformation to be done, if it's there, is reflection. If you have 2 reflections, pick one, do that, and then do the other, and then whatever else. So I want to conclude this section with the final problem of f of x is equal to negative square root of negative x plus 1 minus 2. Now this is a very evil question. Even my calculus 2 always get it wrong, because there is a thing that you have to do before you start doing the problem. All right, let's see if you can figure it out. How many transformations do we have? 4 transformations. Very good. What are those transformations? This is me actually asking someone to tell me something wrong. What are the transformations? It's a trap. Reflection, okay, so we see a reflection here. Perfect. What else? We have 3 to go. We don't have any stretch. No stretch. So, reflection, and you say you have another reflection? Good. So we have 2 reflections. Awesome. What else do we have? Down 2. Perfect. And No, it is down to the 1. Well, what did we memorize that plus is to the left, right? That's true, plus is to the left. But that's not a plus there. This is not a plus. It's a minus, exactly. Very good. The first step in problems like this, where you have this string like that, is to factor out the minus sign, and then it becomes a minus, the shift to the right. That is so evil. That's the next level of evil. Well, and you don't know that because I haven't told you yet, but the first step for problems like this, where you have this situation that a minus sign and then something else here, you have to factor that minus out. So minus square root of minus x minus 1 minus 2, it's a shift to the right, 1 unit, it's a shift down 2 units, and 2 reflections. So you will be using 5 boxes. Default case plus 4 transformations is 5 boxes on your exam out of 6 that are provided. All right, get busy. And then you start the function.
It is to the right. But then since it's exactly when it goes to the left, why not? You're right. Negative equals to the right. Wait, so we will get positive? I thought this already disappears when I distribute it. You distribute it out.
All right, let's take a look at this problem together. We start with the default case and we draw square root of x. That is the default function. Starts at the origin, 0, 0, x, y axis, and we're done. What follows are two reflections. It doesn't matter which reflection you do first and which one you do second. So you can reflect on x-axis first, which is the outer minus, if you want to. So this is negative square root of x. And then you will reflect on the y-axis next, which would give you this. And this is negative root of negative x. So reflected on the x-axis, that's the minus on the outside. Reflected on the y-axis, which is the minus on the inside. And we are at this picture now. The next is to either shift right 1 unit or shift down 2, whatever you want. So let's shift right. We are going to keep the same shape and move 1 and go like this. So that's the 1 unit. So now I have negative square root of minus x minus 1. So that was the shift to the right. And then finally, 2 units down. So this 1 will go 2 units down, and we are going to keep the same shape. 1, negative 2, x and y. This is a point to write on a test. X and y are a point to write on a test. If you go from here to here correctly, it's 100%. If you don't have these in the middle and this is wrong, well, there's no partial credit because there's nothing to put the partial credit on. So you will be the judge on how many of these. I will provide you all with grids to maximize your potential, right, grade. Now you can choose to ignore all of that and just go into the first box and draw the final function. If it's correct, it's 100%. If you put this point as well, an x and a y. If it's wrong and you haven't had any steps before that and transformations, it's 0 points, right? If you populate the boxes in between and the last result is wrong, then I have other 4 boxes or 3 boxes to work on partial credit. Does this make sense? And it makes you happy, right? Right. Now 3 of you. 4 now. 5. Okay. Good. Questions, concerns, issues? Yes.
Can you explain again just the last 2 graphics here? Because I'm confused with the one. Yeah. They go to the right side. Well, what the sign says.
Yeah, so the minus sign shifts to the right. And it's a minus. Minus shifts to the right. So we shifted right. And this minus here shifts down. So we shifted down. We always shifted when we had the minus sign. We always shifted to the left, to the right. There is a plus, we moved it to the left. There is a minus here, and we moved it to the right. You will always take the previous graph and go the next step. 1 transformation at a time, just fine. And always do reflections first. The reason why I'm asking for reflections first is that not everyone is good with what the anchoring point is. You see, over here is easy to see. That's the anchoring point, right? And you start moving and reflecting and shifting, looking at that point. For parabola, it's the minimum value for x cubed is the one in the middle. It's kind of hard to, for some functions, figure out the anchoring point. So reflections become a problem if you already shifted the graph somewhere in the galaxy, and now you're supposed to reflect. Where is that anchoring point, right? Hopefully you see that if I shifted first, the graph would be, if I shifted first, graph would be here, and then I shifted it down, graph would be here, and now you have to do the reflection on x-axis, and this thing is dangling in the air, right? So students usually make a mistake and they draw it like this because it's reflected on x-axis. There clearly is not the answer because it looks like this. So you see the issues of how these reflections can create problems. So my advice to you to maximize this gradient potential here is to do reflections first and then stretch, shrink, move, shift, those kind of things. 1.6 over. No applause? Oh, dang. Tough crowd. Wow.